Hello. In this video I would like to discuss with you double integrals, and I would like particularly focus on the following double integral. That's the integral of a sine function over the following domain. If you inspect closely this domain, you will see that the domain is bounded by two vertical lines and two functions, 0 and 4 cos x. This is a domain in question. So this is a domain which is bounded by the cos wave, the x-axis and the y-axis. If you know a little bit of a double integration, you probably know how to find this integral almost in one line. All you have to say is that the domain omega is so-called y-simple, and when you integrate over y-simple domain, you can convert your double integral into a repeated integral. This is something what Fubini theorem does, and then you can integrate this one after another using the fundamental theorem of calculus. If you do fundamental theorem of calculus first time, it will be 4 cos x, and then you will need to do fundamental theorem of calculus one more time for this function. In this video I won't be presenting the actual computations, but basically this is all you have to do in order to find the integral like this. Things will get a little bit more complex if I change my domain omega a little bit, and if I introduce one extra condition on my domain. Here it is. My new domain, omega 1, is the one which is obtained from omega by introducing this extra control, y doesn't exceed 2. This extra condition means that I have to introduce a horizontal line, like so, and then I have to position this line at the level y equal 2, like so. The domain omega is a domain bounded by these straight lines, then by the arc of the cos wave, and by the horizontal x-axis, like so. If I repeat my question, if I ask what will be the value of the double integral like this over the domain omega 1, such question will be a little bit more difficult than the original question. At this stage you may wonder why I show so much interest in this integral. One possible answer here is that this integral is directly related to bi-convex lenses. Here it is. Bi-convex lens, this is a Wikipedia page on that. It's a lens which obtained by the intersection of two spheres. Sometimes these are the spheres of different radius, like in here, or often it may be the spheres of identical radius. The characteristic of this bi-convex lens, in particular if you try to compute the volume of such bi-convex lens, the integral I showed you at the beginning of this video will be part of your computation. In fact, if you take a special case of bifocal lens, which is the intersection of two spheres of radius 2, like this. On this page I call this omega dash. This is a sphere of radius 2, center, the origin. This is a sphere of radius 2 again, but the center is 2 units up. If you compute the volume of this intersection of two spheres, and if you use the spherical coordinates for that, in the course of your computations you will arrive to a repeated integral of this type. As a part of this integration, you will have a repetition like this, and this is exactly what we observe in my original setting. This is the integral, because the function mean 2 4 cos psi, this is the function which you see here, and the integral which you observe here, this repeated integral of two variables, this is the integral over the domain like so. So this integral, which I showed you on my first slide, it has direct connection to the geometrical characteristics of biconvex lenses. So let's go back to this integral and try to see how we can approach the evaluation of such integral. We can follow the same steps. We can try to approach this domain omega 1 as a y-simple domain. This time, before we can actually present the computation, we need to identify point A on the graph, the one which represents the intersection of the horizontal line with the arc of a sine of the cos wave. So finding that point will involve solving this trig equation, which is equivalent to equation cos x equal a half, and which solves, one of the solution is pi on 3. And this is the angle here, which you observe. This is the angle here, or point here, which represents the solution to the intersection. Now, once you know this point, you can compute this integral in the y-simple terms. You will need to split the integration with respect to x in two subintervals. One of them will be from 0 to pi on 3, and the y control over this interval will be just constant 2, and the second subinterval will be from pi 3 to pi 2, and this time the control will be the arc of the cos function, which is a 4 cos x. This is how you do it if you approach your domain omega 1 as y-simple. Now the objective of this video is to show you that if you know the inverse trig functions, you can shorten this computation by a factor of 2 if you know the inverse trig functions. And I will show you how to do that. So the key to make this computation way shorter than this is to describe domain omega 1 as x-simple rather than y-simple. So I hide back all of the steps we did for this integral, approaching it as y-simple, and this time we're going to approach this as x-simple domain. If I approach this as an x-simple domain, then for omega 1 the corresponding description is like so. First we have to specify the range for y, and we can clearly see what the range is. My y ranges between 0 at the bottom here up to the point 2 up here, and then we have to specify the controls for x. And for x, the control on the left will be 0, but the control on the right, it will come from solving y equal cos 4 cos x equation, which if you solve it, solves x equal cos inverse y on 4. And this is the reason for this right-hand side control for the x value. Now, if you do the repetition, if you apply the Fubini theorem, for this double integral, it will be integral from 0 to 2 with respect to y, right from here. Then there will be an integral from 0 to inverse cos y on 4 of sine x dx, which is from here. And this is something which is very straightforward to evaluate, because the antiderivative for sine is negative cos x. Now once I do the double sub into my cos, the cos function conveniently interacts with the inverse cos and returns y on 4, like so. And in this integral, if you integrate, y on 4 delivers the antiderivative y on 8, which if you compute it gives you 2 take half, which is 3 on 2. I encourage you to finish this computation in a y-simple approach in order to understand how much the usage of inverse cos function makes things easier in comparison to the direct way of evaluating this integral. If you have any questions, please leave them in the comment section below this video. Otherwise, thank you, and I will see you in my next videos.